Who has classes tomorrow? Half of you. But don't come Friday. I'm not coming out here. Yeah, last day of class is Thursday. I particularly like when instructors ask me for demonstrations like Friday. I'm like, Why do you? And they get upset. You don't have class. Yeah, I do. Go look it up. Nobody will be there. All right, when's the final? Tuesday the 13th at 10:30. Here. All right. Do you guys, you come up with any questions? Am I going to pass? Who said that? You said it? Yes. Most people pass. People that have come to class and done the work. I didn't say how well you did the work, and done the work generally pass. There's several that probably won't pass, but they're probably not here. Yeah. Any other questions? Okay, just in case you guys were studying and came across something. Well, I think we left off with momentum and collisions. That was chapter 6. We redefined that momentum is like inertia in motion, mass times velocity. So you have to pay attention to mass and velocity for momentum. And if you're going to change something's momentum, you got to apply a force to it for a certain amount of time. That will change the momentum. We call that impulse. Then things collided. What two types of collisions were there? Elastic and inelastic. And what's the difference? Yeah, basically, if they stick together, it's inelastic. If they bounce off each other, it's elastic. In which of those two is momentum conserved? Both. Good job. It was a semi-trick question. Now, conservation of energy. In which of those is energy conserved? You guys didn't sound as confident on that one. Yeah, total energy is always conserved. It was a semi-trick question. Total energy is always conserved. Kinetic energy, or as the book referred to, mechanical energy, kinetic and potential, that's not conserved in an inelastic collision. Where does some of that energy go? Yeah, to crumple. Think of two cars crumpling together. They might not even stick to each other, but they'll crumple. Two football players tackling each other. In reality, every collision is slightly inelastic. There is no such thing as a perfectly elastic collision, but we idealize. Because in theory, in any collision, there's always some of that energy you don't get back in the form of mechanical energy, kinetic and potential, because it goes to heat or work done for deformation or light or sound. All of those are energy. So, total energy is always conserved, it just gets transformed. In an inelastic collision, the kinetic energy might be less afterwards. If you're traveling yay fast and you hit something, you'll probably be, and it's inelastic, you'll probably be moving slower now. But momentum's always conserved. Do you remember how to find work? That's right. You apply a force to change somebody's momentum, to change its motion, make it accelerate and change its velocity, and that takes a certain amount of time. Impulse was force times time. But that also acts over a certain distance. That's work. Force times distance is work. So I push on something, it moves a meter. There you go, my force times a meter, that'll tell me how many joules of energy I just exerted. And that will change. Did you see what happened? It's subtle. You're probably thinking, duh, now that you've had a whole semester of physics. Whoosh, I applied work, and it changed that rag's kinetic energy. I got it to move while I was applying work. If you remember, that was the work energy theorem. Anyway, it's just, that's what it was called, but it's just relating that the work network, because you could have more than one force. If you combine them all, everything that's acting on it, causing it to move, that will change its kinetic energy. Just an equation to sum up that what I hope you think by now is duh. You push on something, it's going to move. So,
what if you push on it and it doesn't? Like the wall.
Okay, you tell me. I'm pushing on the wall, aren't I? Are you convinced?
Yeah.
All right. How much work did I just do on the wall?
None.
0. I didn't move it. So did I exert energy? Yes. So I did work. There was some chemical work. My muscles did work. But I did no work on the wall. The wall didn't move. So I didn't change its kinetic energy. What is kinetic energy? It's the energy associated with motion. And the equation, 1/2 mv squared. There's that squared term again, so that should be a tip-off that, hey, this isn't linear. It's not a, you double the velocity, what happens to the kinetic energy? It does not double. It quadruples. Remember, like the practical application? You're tooling down the highway at 95 miles an hour, shame on you, and you slam on your brakes. You apply a force for a certain time to change your momentum for a certain distance. So you're doing work on the car to slow it down, to change its motion. It decelerates. It slows down, so its kinetic energy decreases. What's actually doing that work? What physically slows you down? What's the force being applied that's actually slowing your car down? You hit the brakes. Friction. Friction.
Friction of the brake? Friction of the road?
The brakes, well, your car is moving. You hit the brakes, it causes friction, you know, it pushes on the hydraulic fluid. There's Pascal's principle. Pascal's principle in fluids was a force will be equally transmitted in any enclosed container. That force is acting on the area. Pressure is force over area. I'll go ahead and write that one down. Pressure is defined as force over area. So you apply a force over the area of your brake line, because that's the fluid in there, and it's transmitted through that over to your brake pad, which might be a different area. So you'll get a different force out. Simple machine type of thing. But energy is conserved. That'll squeeze the brake pad or the rotor onto your disc, depending on how it is. Anyway, they push and there's friction there, so your wheel can't spin anymore. But your car's still moving because of inertia. But now it's sliding on the ground, and the ground exerts friction on the wheel. Your car's moving, your wheel's moving with it. The brakes just stop your wheels from rolling. So then the ground can push on the tire and actually stop you. It's the ground, the friction from the ground pushing back on your tire. If you want to exert a force to slow your car down, the force has to be on the car. That's the pavement on your tire. My point of that was, okay, that's the force that slows you down. So you just did, that's the work done by friction to change your kinetic energy. All right, so now you go twice as fast. How far will it take to stop you now? 4 times as far. So just by going a little bit faster, it's going to take you a squared factor more distance to stop because energy is conserved. What's gravitational potential energy? That's the energy associated with position. So it has something to do with position in there. mgh. What was mg referred to as? Yeah, that's your weight. That's a force. You're trying to move something up and down. You got to counter its weight. And you displace it a certain distance. Look, a force times a distance. That's work. It takes work to lift something. We had simple machines. They don't magically create or destroy energy. What can they do, though? Multiply what? No, they don't multiply or divide energy because energy is conserved.
It means you have to do less work. Right?
Work is how energy is transformed. So you can't like do less work. That would get rid of energy.
So you,
It does do something. There you go. The distance could change. And if the distance changes, then the
you need less force.
force, you can multiply or divide the force needed to pull off that energy. That was this game. A simple machine does a certain amount of work. You do a certain amount of work. Just think of a lever. It's a simple, nice simple one. You got something really heavy over here, so what do? You put a lever, and so you push over here. You push down with a force, right? If you apply that same force directly to here and try to lift it, you can't. This is too heavy. It's like a piano, let's say. But I can apply a force over here and move a greater distance. Over here, I won't move it very far, little distance, but I'll get a lot more force out. So it's big F, little d, little f, big D. So you can multiply or divide the force and or the distance depending on what you need the machine to do. But the energy is the same on both sides, the input and the output. Ideally, anyway. That's what simple machines, that's what all machines are trying to do. Get the same energy out that you put in. Reality sets in, though, and they don't. What do we call that? If you get a little bit less out than you put in, I heard somebody say it, that's what efficiency was. If something's only 50% efficient, then you're losing half of the energy you put in. It's going somewhere else, not how you want it, like heat or sound or something. 100% efficient machine, you get it all back. But there is no such thing in reality. Is this all coming back to you? Like, oh yeah, oh yeah. We shot objects in 2 dimensions. All this motion stuff, now we just started going up and this way. Remember I shot something over here? What do you remember from that? I did a projectile. It has an upward component of velocity and a horizontal component of velocity. So which way does it go? Point. Remember vectors and components? Yeah, it's going to go that way. And if I shoot it higher, that means the vertical component of velocity is greater than the horizontal. What will it do? It'll go higher. How about its range, the horizontal distance? Yeah, it'll be less. And vice versa. And last, these compare how? Do you remember that special case? They'll go the same distance if the angle you shoot it is... if they add together to equal 90. So you could set it, you could aim it at 30 degrees and 60 degrees, and it'll go the same distance. Why? Because you guys just told me, wait, 60 degrees would be more like this, shooting it higher up. It goes higher, but not as far. But 30 degrees, okay, 60, 30. Yeah, it's the hang time. This one's going faster that way, so it should get further, but it doesn't have as much time to do it in the air. This one doesn't go as fast that way, but it's in the air longer. It has more time to get there. So if the angles add up to 90, they do go the same distance. If you shoot it at 75 degrees, that won't go as far as 60. But 75 and 15 will end up in the same spot, both being a little shorter than 30 and 60, which are both a little shorter than 45. But that's that component game. Remember our cougar shoot? What was the key point about that? That big wood bullet. Remember it hit?
That objects always fall like at the same speed.
See, you learned. I know you have it right, but your one word was incorrect. Acceleration. So if here's the bullet, it comes out with a certain horizontal velocity, and you got monkey, cougar, whatever, we'll just, with no velocity initially, and you just, remember it lets go at the same time this came out. This will come along and it'll be a little further this way. And then a little, and then where this one, well, let me note something. I tried to have it go the same distance horizontally because it's a constant velocity in the x direction, so its displacement horizontally is consistent. Its change in position is the same with each second. But notice vertically, it accelerates. And so the spacing increases. Well, the cougar should do the same thing because he accelerates at the same rate of gravity. End up here, and then there. That's why they hit.
But that's only if the bullet was shot at the same height and is at a tilt, correct?
I shot it at a tilt. I'm pretty sure I did. So I aimed it up. And as soon as it came out, it let go. Did it hit it? So it still works that way, if you're aimed right at it. If we turned gravity off, what did I do? 1, 2, 3 seconds? 3 units of time. After 3 units of time, it would be right here. So it's as if it started there, because at this whole time it's moving that way, it's going to accelerate at the exact same rate as that accelerates vertically. So vertically, they will end up in the same spot. It'll do that thing. But yeah, the key is because they accelerate at the same rate. Yeah, I drop a big object and a small object. You know they hit the ground at the same time. Why? Because the acceleration's the same rate. It takes them the same time to get there. So which one's feeling the greater force? Or are they? They're not feeling the same force? If they get there at the same time, how do the forces compare? I've asked you this lots of times this semester. Which one's heavier? Use your common sense. Which one's heavier? The rag. So the force of gravity. The Earth is pulling on the rag with a greater force. Why does it need to pull on it with a greater force? Because it weighs more. It's got more inertia. F equals ma. To have the same rate of acceleration, 9.8 meters per second squared, 10, it has to pull on the heavier object with more force. But yeah, just use your common sense. This is heavier, so the force on it is bigger. It's not that the forces are the same when you drop things. It's because they accelerate at the same rate. Theory of relativity. What do you remember about it? That it was hard and confusing? See some takeaways. It was based on two postulates, that the speed of light's a constant in any frame of reference. Everybody gets the same value, whether you're moving or not, which is different from our common sense. Remember, if I'm on a train moving at 10 meters per second this way, and I throw a ball at 50 meters per second that way, what's the speed relative to you? 60, because you're at rest. The train's moving at 10 with respect to you, and I add 50 more to the ball. Yeah, it's 60. If I throw it the other way, it'd be 40. They add and... Yeah, for me on the train, I'm moving with the train, so it's only moving 50 relative to me. Different frames of reference. And remember, they're both right for their frames of reference. And the other postulate is basically that all the laws of physics that we've just been learning are true in any inertial frame of reference, as long as that frame of reference isn't accelerating. Given that, and that the speed of light's a constant, we had lots of fun consequences. Name one. Anybody? The funky stuff about relativity. It had something to do with lightning, yeah. What about lightning? Yeah, simultaneity we called that. People could see different events occurring at different times. One person in one frame could think event A happened before event B. In a different frame of reference, he could see it the other way around. They're both right from their frame of reference. So what's simultaneous in one frame doesn't necessarily have to be it in the other frame. What was another weird consequence? Yeah. Yeah, aging. Time dilation, we called it. Times were different in different reference frames. Remember our light clock? If we just saw a light pulse go up and back down, great. It covered that distance and that time. It's at rest with respect to me, the clock. I get a time. But if I take this clock on a spaceship and let it whiz by me, whew, now you're seeing the light beam, it's going up and down. Remember, it's got that horizontal and vertical component. It'll travel a farther distance and do it in a different amount of time. That time dilates, it slows down. For those moving relative to you, it appears that their time dilates or runs more slowly. Hence that twin paradox where one ended up younger than the other. But what's connected with time? Blank time. Space. There's another thing about relativity. Space-time, it's like one thing now. There's not space, there's not time, they're like one thing. So they go hand in hand. So if time adjusts, time dilates, what else happens? Space contracts. That was called length contraction. So for an object moving relative to you, it looks shorter to you. It contracts in the direction it's moving. Those were the two funky things about relativity. Let me refer to the test here. Before I continue on, look at some questions. Yeah, can you balance net forces? We did that last time. If you got more than one force on something. There's a few questions about that. You might say something sliding. If Earth's pulling it one way, but friction's holding it back, you just balance the forces. Or if one's bigger than the other, you'll have a net force and it'll accelerate one direction or another. With those collisions, look at your problems where you had a few numbers. They were simplistic, but if you have a ball coming in, and this one's not moving, and then they hit each other, and there's speeds afterwards. Can you do that? Whether it's elastic or inelastic? Remember we said the momentum's conserved? So you find this guy's momentum, that guy's momentum. That's the total momentum before the collision. That has to be the same after the collision. So M1 V1 final plus M2 V2 final. And I'd have to give you enough to solve that or something, but yeah, it's distributed. If they stick together and it's inelastic, then they're both moving with the same speed. But again, the total momentum after has to be what it started at. Same with total energy or kinetic energy in an elastic collision. Do you remember we did like roller coasters too with energy? I don't know. Total energy everywhere has to be the same. So if you start way up here with all gravitational potential, you get down here, how much gravitational potential energy do you have here? Zero. Where'd it go? It's all kinetic. How much kinetic? The same amount you started with. What do you have here? Both. It depends on the height. Yeah, the way I drew it, yeah, if that's to scale, yeah, half-half. It's still moving there, but it still has height. So yeah, it's both. But, so here it's all kinetic. Here it's gravitational potential and kinetic. But the total's always the same. There's a question with that, the time in the impulse equation. You can change the force needed with impulse. Remember? How can you make something hurt less in a collision? Make the collision take longer. Right. That's why you wear helmets. Because if you make t bigger, the force can be smaller for the same impulse, for the same change in momentum. If you're going to stop it anyway, let's just make it easier. The Lorentz factor, that's what I was thinking about when I got to it. So time dilation was related to a Lorentz factor. I just brain lapsed. Don't want to write it. That's why you get your cheat sheet, right? Concept's more important than... Yeah, it was a 0 over here. Remember that Lorentz factor? That was the ratio of 1 over the square root of 1, blah, blah, with the speed of that you're going relative to the other frame over the speed of light. It looked big and scary. You can write that down too. But if the Lorentz factor is 2, then time gets slowed down by a factor of 2. The lengths contract by a factor of 2. Momentum changes by a factor of 2. Energy changes by a factor of 2. All based on that Lorentz factor. I don't intend to make you calculate the Lorentz factor, but given it, you should know those effects. So if momentum is normally just mv, your relativistic momentum would change by the same factor, depending on how fast you're going. That's what the factor tells you. So that time dilation and length contraction and change in momentum and energy can all be determined by that Lorentz factor. In a spaceship, or satellites, more practical. Your cell phone satellites, in order to get your signal, if they do not account for that, then GPS is useless. The times are too far off. Your positions are too far off because they're whizzing around not extremely relativistic. They're not really that fast compared to the speed of light, but they're a lot faster than normal everyday velocities. And so there is an effect, a noticeable effect that our GPS would be off if we didn't account for it. The time does dilate.
But then your equation doesn't really change.
Which equation doesn't change?
So like, how would you plug it in?
Well, before it's like time in one frame is the same time in the other. That's why the events look simultaneous. But relativity now says if one of those frames is moving relative to the other, this tells you the relative motion between them, the different speed. And so now the times won't be the same. The length won't be the same. The momentums won't be the same. So a clock, if I took my watch and put it on one of those satellites, it would run more slowly from compared to how it runs now on my arm. If I looked at it from here, if I stayed here and looked at how fast it ran on the satellite, it would appear to me to run more slowly. It would also contract in the direction it's moving and look shorter or thinner.
The same thing if you were to look at a watch in space, it would look like.
Yeah, if you were on the satellite. But let me go to the satellite and take a free ride and look back at my watch that I left down here on Earth. Well, it's moving relative to me. I'm up there in the satellite in that frame of reference. To me, I'm at rest. And the Earth, my watch, is what's whizzing around. So I would see that its time slow down and its length contract by the same factor, that factor of our relative motion between us. This prompted any questions of your own yet? Do you remember the term mechanical equilibrium? What's equilibrium? We say something's in equilibrium when? When what? The net force is zero. Can it be moving? Yeah. There could be dynamic equilibrium where it's moving but at a constant velocity, or at rest. Static equilibrium. But yeah, equilibrium is when the net force is zero. Things are balanced. Did you have a question, Tina? I thought I saw your hand go half. Okay. Let's see, what else can I help you review? We need to do some fluid stuff. We did pressure. Do you remember density? I encourage you guys to review that test. I think on average that was the worst test. Wasn't that much worse.
The third one or the second?
The one on fluids, which is the third one. Fluids and electricity. Density. Mass over volume. And pressure was force over area. Like your snowshoes on the snow versus high heels. Same weight, but if you exert it over a different area, you get a different pressure. Pressure was Volume or depth dependent? Did pressure depend on? Good job. It was the density, gravity, height. There's the depth. How deep you are below the fluid. How much fluid is above you. So in water, it's when you go scuba diving. That's why we think of depth. But in the atmosphere, with gases, it's how much is above you. You're like in a big sea of the atmosphere. You go down. So the more above you, that creates pressure down at that depth. The pressure here, not the hole, the pressure there is greater than the pressure there because you got more on top of you. So water shoots out faster there than it would here, right? Sinking and floating. What determines if something sinks or floats? Density is one way to look at it. Okay, let's look at water. When will something sink? If it's more dense than the water. If it's less dense, it floats. What if it's the same density? Neutrally buoyant. It doesn't go up nor down. And that's all true in the air too, for like helium balloons. Are less dense, so they rise up. Now let's do the same thing with forces. Something sinks when? Yeah, there was a buoyant force, and there's its weight, which was mg. The buoyant force, I'll write that one in a moment. If they're equal, we have neutrally buoyant. It doesn't go up nor down. If it's not moving up or down, that includes floating on top of the water. You know, you got a cork here. The forces are balanced because it's not going up or down. So the buoyant force balances its weight. What if the buoyant force is larger than its weight? It goes up, and vice versa. So this one, if it's floating there at the top, then that equals that. What determines the buoyant force? What's it dependent on? I heard lots of things, yes. Oh, right over here, clear. It was dVg. That one's volume dependent. Archimedes' principle was the buoyant force is equal to the weight of the displaced fluid. You jump in a swimming pool, you displace a certain amount of water. If you could capture that water and weigh it, that's the buoyant force on it. It's the weight of the displaced fluid. So I take up a certain amount of volume in the atmosphere, sometimes more than I want. The weight of the air I displaced is my buoyant force. Is my buoyant force bigger or smaller than my weight? Smaller. That's why I sink in the atmosphere. But a helium balloon can displace a certain volume of air, and the weight of that air will actually be more than the balloon's weight. So that's why it goes up. This is bigger for a helium balloon than that. On your notes, this is the density of the object or the fluid? Fluid. Because it's dependent on what fluid you're in. Remember salt water versus fresh water? The volume is what? The volume of what? Not always the object. Displaced fluid, good. Displaced fluid. Because like this, it's this much. That's all the fluid it displaces. That's all the fluid it needs to displace to float. That's not the volume of the object. If the object's completely under the water, then they're the same. And gravity is what you're used to. So pressure is depth dependent. Buoyant force is volume dependent. And you know, if you jump in a swimming pool and stood on a bathroom scale, you'd weigh less, right? Because the water is helping buoy you up, hold you up. So you're not pushing down on the scale as much as you are in the air. That difference in weight, what do you think it is? The buoyant force. Let's think of some ones that stumped you initially. I remember. Oh, how about the life preserver? I throw you a life preserver. I like this one. One of styrofoam or an identical shaped one full of lead. And I yell to you, hey, they have the same buoyant force. You'll be just fine. What do you say? You want the styrofoam one. Why? It weighs less. Okay, but am I wrong? No, I'm not wrong, because if they're the same size, they displace the same amount of fluid. And so they will have the same buoyant force. A lead-filled life preserver versus a styrofoam-filled one. But let's look at this now, whether you sink or float. They have the same F. Yeah, but lead, this will be huge, so you'll sink. So it's useless. Yeah. It's worse. Styrofoam doesn't weigh very much, and so this will be smaller than the same buoyant force, and you can stay up. So buoyant force is volume dependent.
So what you're saying is like a brick can have the same buoyancy force as like wood? It's like
Yeah, you could have a brick and a piece of wood the same size. They would have the same buoyant force submerged under the water because they would displace the same volume of water. But because the brick is heavier, that buoyant force isn't sufficient to keep it up. There's still all the stuff from the last unit on waves. I've just kind of intentionally been avoiding that since it was the most recent. We just went over it. But if you got questions. Do. Yeah, that's on there. Let's see. We'll end with that then. Electrostatics and electric current. Coulombs Law. Was just the force between charges. Well, charge 1, charge 2. Is there a force between them? There's a gravitational force because they have mass. But because they have charge, there's also this electric force, the Coulomb force. And it was, where r is the distance between them. K was that constant of proportionality. So it's based on the charges. How does the charge that Q1 exerts on Q2 compare to the force that Q2 exerts on Q1? They are the same. What law is that? Newton's third law. All forces come in as a pair, as an interaction. But what if I do this? What if I make this a whole bunch of charge and leave this one the same? Same distance. Now whose force is bigger? I heard only one vote. Good. They're still the same. Bless you. Because look, you'd put in the charge for the first one. You put in the charge for the second one. That tells you the force between them for each one. So if I make this charge bigger, it makes the overall force between them bigger, but it's still the same for each one. Just like with mass. I'm about 160 pounds. So what's the force the Earth pulls on me with? 160 pounds. That means it's pulling me down with. So what force am I pulling it with? Yeah, I exert 160 pounds of force up on the Earth. It's huge. But see, the action-reaction pair is still the same force. Now it has less effect on the Earth because of Newton's second law. It has more inertia, so we don't see it move. Technically it does, but that much. Same idea with Coulombs Law and that the forces between charges. Charges have electric fields around them. Do you remember which direction they go? Electric fields? Positives and negatives. They go away from positives and towards negatives. So they're going to end up doing something like this. Yeah, those are the electric field lines. There's electric fields out there. Electric field was defined as force per charge. Because we got lots of charges. We don't want to keep track of them all. So this helps us sum it all up. It's the force, this Coulomb force, but per charge. Then we had voltage. Remember what voltage was? That was energy per charge. It's how much energy per charge it had. And the voltage is what started pushing those charges around, and they're accelerated by the electric field. And with this analogy, force is mass times acceleration. That electric force on charges is the charge being accelerated by the electric field. That's just rewriting this. In circuits, it's that voltage. You give them a certain amount of energy per charge and they get pushed through the circuit. How much that flows is the amount of charge that goes by in a certain amount of time. It's the rate the charge flows by. And then we did that in circuits, but I ran out of time. So go review series and parallel.
What was the I?
Current. Current. That's the flow of charge. That flow rate of charge. They're getting pushed by Coulomb forces, accelerated by the electric fields. And how much flows is the current. Okay. If something comes up, contact me. You have a week to think of things and study.